Good morning, good afternoon, good evening, mammals. This video is going to be for NTI day number 5, which is Tuesday, March the 17th. I'm going to talk about the rest of the things that you need to include in your lab report and give you some examples what to talk about. If you've got any questions, you can send them to me on Google Classroom, or you can go ahead and submit your lab report as a draft, and I can make some comments and send it back to you, and we can go from there. So first thing is the objective. That's always just a one-sentence statement. I'm perfectly fine with you using this statement here because it's what we did. The introduction, I'll go through kind of point by point. We got 3 main things that you need to talk about, and then you can kind of paraphrase that and put it into your own words. So for the first one, we're going to be dealing with a big misconception that a lot of students have about the difference between concentration versus strengths of acid. Because in our regular language, we might kind of use those two interchangeable. But concentration is purely just referring to the molarity, or the moles per liter. It's entirely independent of strength, because you can add whatever amount of acid to whatever amount of water that you want and get different acids with different concentrations. The strength, on the other hand, is referring to the acid's equilibrium constant, and it's expressing where the equilibrium position is for an acid doing its thing, which is ionizing and producing protons in conjugate base. So stronger acids with higher Ka's lie further along the right of this reaction, where they're predominantly products, so mainly hydrogen and conjugate base, whereas weaker acids lie further on the reactant side and are predominantly acid. And then of course we've got the category of strong versus weak. Strong simply means that this equilibrium is essentially infinite and it goes completely towards products. A weak acid is a category where we have an equilibrium. It's just that this equilibrium is something less than complete, where we have something there. So concentration is molarity, strength is dealing with the equilibrium constant, and then strong versus weak is just whether we even consider the equilibrium or not. So if you think about that, you can describe a situation where a weak acid could have a lower pH than a strong acid, and that's because you have to consider the concentration with these. If I have a very, very, very dilute strong acid, I'm going to have a pH that's approximately 7. You know, if I put 1 drop of HCl into 3 liters of water, it's mostly water and it's going to be ever so slightly less than 7. Whereas if I have a very concentrated weak acid, my pH is going to be somewhat less than 7, because even if the Ka is very small, if I put enough of this in there, it's going to drive the reaction to the right and produce a significant amount of proton, giving us a low pH. Okay. Next topic is what's present for a weak acid at different points along the titration curve. And this is going to be a biggie because it kind of reflects the things that you might be asked about on the AP as to what's present in a solution that's being titrated at any point. So I'm going to get some space here, and we're going to consider these 4 points along a titration curve. So sketch me up a titration curve here. Make it weak with a buffer zone and an equilibrium point that is above pH 7. Okay, so the initial point. At the initial point, before we've added any base, what is present is just the acid itself. Now it has somewhat done its thing, even if it's a weak acid, and dissociated, making protons in conjugate base. However, since these are weak acids, all of them have pretty small Ks, it's going to be predominantly this, and the amount of these are going to be really, really small. You know, they've got to be there because we have a pH less than 7, so they're there, just not very much. And the AP questions along these typically ask like what species are present in, amounts more than 0.1 molar or something along those lines. And that's just getting you to not talk about the lesser species. You need to understand conceptually that they're there. They have to be there to have a pH less than 7. They're just not the main thing. Okay. Next place, the half equivalence point, which is going to lie about right here. We're right in the middle of that buffer zone, and that's the special place because we have reacted half of our acid with added base so that we've neutralized half of it into conjugate and water. And since we've eliminated half of this, what that means at this point is our acid equals our base. Because we've converted exactly half of this, we have half of it remaining, into this. Now the other thing that people forget that's also present here is going to be the counter ion of whatever the base is. So I'm going to use sodium here like we were using sodium hydroxide. But these three things are all going to be equal at this point because we had to add half the amount of base to convert this. So these are all equal at this point. Okay, equivalence point. We'll do kind of a twofer here because I'll be mentioning about why this equivalence point is going to be above 7, which is your last topic on this. So at the equivalence point, we have added equal amount of base as our acid initially present. So that means we have used up all of our acid, and there's no excess base left over right now. So that means we have turned everything into conjugate base. So at this point, our main species that is present is just the conjugate base. And the counter ion. These are going to be equal to each other. The other thing to consider, though, is that our conjugate base is a base, so it's going to do its thing, and it's going to steal a proton from water and reform our acid, making some more hydroxide, which is why our equivalence point pH is going to be greater than 7 at this point. But just like in this situation where we said, we're not really going to consider the H plus and the A minus in the initial point because this has a very small K. Similarly here, this has a very small Kb, so the amount of HA and hydroxide present are inconsequential compared to the amount of conjugate base and counter ion. They have to be there again because we've got a pH greater than 7, but if you were asked what are the major species present, just these guys. And lastly here, the past equivalence point. We have completely converted all of our all of our acid to conjugate base at the equivalence point. So there's no more of this left to react. This is already a base, so it can't really interact with this as a base. It can't have any more protons taken away from it. So all we're doing past the equivalence point is just adding excess amounts of our strong base. So that means after the equivalence point, we are now going to have greater amounts of counter ion than we have conjugate base. There's not going to be any acid present. We've still got just these two things that are present, and this one now is going to be greater than the conjugate base. Now we do have some hydroxide present, and I guess if you add enough of the base, you could have appreciable amounts of hydroxide present, but the main species are this. Okay, let's go up to our last question. We'll see that I've kind of talked about it already. The last thing to talk about is why is the equivalence point of a strong acid 7 and a weak acid greater than 7? So I'm going to go back to our discussion down here that we've already had. For the weak acid, you're producing a weak conjugate base, which will have an equilibrium with water to reform the weak acid and some hydroxide, so the pH is greater than 7. If we titrated a strong acid, so this is strong, our chlorine could be thought about as the conjugate, but if we have a strong acid, the conjugate of a strong acid is neutral. So what is not going to happen is the chlorine cannot retake a proton back from the water to act as a base. So this reaction does not happen. And since it doesn't happen, we just have water at the equivalence point. So we get a pH of 7. So that'll let you answer why the weaks have a pH greater than 7 and strongs produce a pH of 7. Okay, let's go on to our last slide here. Talk about the conclusion. Okay, how did you determine which acid was strong or weak? Like we talked about in class, you know, if we had lots of money, we'd have pH meters and we could look at the titration curves and see if we have that buffer region or if it just stays low. So you could tell weak versus strong. But even with that pH paper, you should still have enough that you could see that one of them hung out here at pH 1 or 2, basically until you got real close to the equivalence point, while the other moved gradually upwards. So it's just our proxy for the for an actual pH meter, but it's good enough. Phenolphthalein has a pKa of 8.7, so that's when it's going to be at pHs greater than 8.7. It's going to be 8 point. Come on, give me a point. It's going to be pink. And you know, this obviously is not exactly our equivalence point pH, yet this is still an okay one for that. In our notes, we had some discussion about how this is going to be our strong with a equivalence point, a perfect equivalence point of 7. And we're turning pink somewhere here above 8.7. Give me a point. And so the true equivalence point would happen at this volume. Your observed equivalence point is happening when you get to this volume. But of course, since we've got such a near vertical line here, the amount of difference between those 2 points is going to be insignificant. So that needs to be your discussion point there, that as long as the indicator is occurring and is switching colors on the vertical part of the titration curve, you're going to be fine. Now if it's indicating somewhere down here, you could have an error, and that's not going to be a good indicator. But for this one's good. And lastly, kind of an error analysis question here. Sodium hydroxide can react with carbon dioxide in the air according to this net ionic equation. Sodium hydroxide is actually really good at capturing carbon dioxide from the air. So the question is, what is going to happen if a student used sodium hydroxide which has been left open for a long time? So if it's been left open for a long time, this reaction is going to have had a while to occur. And what that's going to do is that is going to use up the sodium hydroxide. So sodium hydroxide's true molarity, in the lab we were saying that our sodium hydroxide was 0.1 molar. But if it was left out in the open, it is going to be something less than 0.1 molar, because some of that sodium hydroxide would react to form carbonate and water. So think about what's going to happen. Is the student going to have to use a greater volume of sodium hydroxide or a smaller volume of sodium hydroxide because the concentration is now something less than what it should be? And because they're using a different volume, what's going to happen when they calculate, assuming that the strength is actually this when it's something less? What will that do to their calculated strength of the acid? Okay, sorry this is so long-winded, but this is a pretty full lab report. I hope it's not the last full lab that we get to do. I hope we're back and get to do some things, but we'll take it as we come. If you've got any questions, post them to me on Google Classroom, and you can go ahead and submit a draft of this, and I can comment on it and send it back to you if it needs some major changes, and we'll get polished up so that you can have a good summative grade. So that's that for today. As always, take care of yourself and others, practice good hygiene, and I'll see you on the flip side.